So before we go any further, I want to be really clear about terminology here, especially in this particular section of the course, but also when we talk about greedy algorithms. I'm going to use the term optimal a lot. Okay, so if I say an algorithm is optimal, I'm using that as shorthand, right, as kind of a condensed way of saying the algorithm returns the optimal solution to the problem, right? In other words, the algorithm solves the problem exactly, okay? And so I might also use the word exact sometimes. In fact, I think I used the word exact in your second homework to describe what the greedy algorithm for the knapsack problem is not. So if I say an algorithm is optimal, what I generally mean by that is that the algorithm solves the problem exactly, which means that it doesn't miss the best possible solution to the problem. Okay, what optimal does not mean is that it solves the problem as fast as possible. Okay, so optimal is with respect to solutions to the problem, right? How good is the solution to the problem, such as how short is the path, or how low is the cost of the path in this shortest path problem. Optimal is not with respect to the time it takes to solve the problem. So optimal is not about time. Okay, we will talk about like the fastest possible algorithms for solving certain kinds of problems right near the end of the course. But for the most part, what we're going to be using the word optimal for is not anything to do with time, but it's something to do with whether or not it's getting the exact answer to the problem, right? Does it actually, like if I'm asking this algorithm, what is the shortest path? Does the algorithm just return like some path, or does it return a guaranteed shortest path? Okay, so that's what optimal means. All right, so let's think a little bit about, first, why is exhaustive search doing so badly? Like, why does exhaustive search take so long to solve this problem? And then in conjunction with that, how can we exploit some structure of the problem to solve it faster without missing the optimal solution, right? Without missing the exact lowest cost path. So suppose I came to you and I said, hey, I found the optimal path in this graph, and here it is. Let me tell you the optimal path in this graph. It starts by going middle, and then it goes middle, and then it goes up, right? And then it just takes that to the end. So I'm guaranteeing you that that's the optimal path, right? So blue is optimal. And then I ask you this question. I ask, what is the optimal path from here to the starting node? Right? So suppose you know that the blue path is the optimal path from green to red, and so this is from green to red. And then I come to you and I say, given this, what is the optimal path? So here's my question mark. What is the optimal path from yellow to red? You would say, well, it's just this, right? You just follow the rest of the path that you already gave me, right? And I would say, well, why? And you would say, well, if there was another way to get from yellow to red, then it would be part of the optimal path, like a faster way to get from yellow to red, then it would be part of the optimal path you gave me in the first place. And so if you were correct in saying that the blue path is the optimal green to red, then I am correct in saying that blue, just following blue, is the optimal path from yellow to red. Okay, and so this is a core principle of something that makes dynamic programming, or DP algorithms, work. And I'm going to write it down like this. I'm going to say that the tails of optimal solutions are optimal. So if I give you an optimal solution, right, if I give you the blue path, then that blue path contains a bunch of optimal solutions to subproblems, right? In particular, it contains the optimal path from this node to the end, and from this node to the end, right? So just giving you an optimal path from the start to the end contains a bunch more information, right? It conveys more information. So this is called the principle of optimality. Principle of optimality. Okay, the principle of optimality is, and this isn't something that all problems have, right? Not all problems obey the principle of optimality. This particular one does, and if a problem does, then the dynamic programming algorithms are a good approach for that problem. So the principle of optimality says that the tails of optimal solutions are optimal. Okay. All right, so let's think now about how we can use this to throw away a bunch of the work, a bunch of the extra unnecessary work that the exhaustive search algorithm is doing. So take a look at this diagram again. Okay, and now suppose I were doing the following. Suppose I had the notion that rather than enumerating all paths, I was going to start at the end and work backwards, right? So I was going to start at the end, and for each stage that's penultimate, right? So each stage that's close to the end, that's second to the end, I'll find the shortest path just by brute force from that particular stage to the end, right? And so what'll that do? Well, that'll give me a policy from each. Oops, not police. It'll give me a policy from each of these nodes that tells me what to do going forward, right? It'll give me a plan, right? And so suppose that plan includes, hey, follow this yellow path. That's not showing up at all. Let's try. No, that's fine. Nothing's going to show up because I've got it kind of inverted and it's strange. So suppose I've got a plan that says follow this. Yeah, red doesn't even show up. Follow this yellow path to the end. Okay. And so now let's think about how that plan would let us save some work that the exhaustive search algorithm would still be doing. So some of the paths that the exhaustive search algorithm looks for include this one, right? Include the optimal. So if it's enumerating all paths, it'll find the optimal path, but it also will it'll also find this path, and it'll also find this path. Okay, so suppose that if we had determined that the yellow path was the optimal path from this, from this node, right? That the yellow path was the optimal path from this node to the end, then what that would let us do is not have to consider all three of these paths. It would let us ignore this one, because we know that once you're at the yellow node, you're not going to go down anymore, right? So it would let us ignore this one, and it would let us ignore this one, because the fact that yellow is optimal lets us ignore the fact that you could have started at green and gone just middle, right? So just knowing something here at this second to last node about the optimal path going forward actually lets us save work earlier on, and lets us rule out several paths that we otherwise would have wasted time searching for. Okay, so let's move forward now with this notion that maybe what we need to be doing is solving subproblems and then using the solutions to those subproblems to put together a solution to the overall problem. And so in dynamic programming, or in DP, this is the key step that is kind of the trickiest to get your head around at first. The key step always involves identifying a smart subproblem to solve. And so the subproblems that we're going to solve for this particular routing problem are the optimal paths of the tails of our solutions. So we're going to build up all the optimal tails and then use that to take another step and take another step, and we'll essentially start at the end and work our way backwards to build up an optimal solution to the overall problem.